What is a quadratic and how do we recognize one? We'll discuss that in this video and we'll see how we can solve quadratic equations by factorizing them. Let's start off with this example. A stone is thrown directly upwards from the top of a 250-meter tower. Its height above ground level is recorded at 1-second intervals. When does the stone hit the ground? In order to answer this question and other questions, we can use the table of values that we have already recorded. We can draw a graph of the situation, or we can model the situation with an equation. We can plot the data and get a graphical representation of the relationship. We're asked when the stone hits the ground, so the height is 0 there. So really what we're looking for is where that graph will meet the time axis. If we extended that curved line, it looks as though it's heading towards 10 seconds. We can approach it algebraically by getting the equation of that curved line. Now we saw that it has to be a squared relationship, and we can put the data into a computer package and it can give us the equation, but we can also find out manually by finding the coefficients of the t squared, the t term, and the term without the t. That is the -5, the 25, and the 250. There are three things we're trying to find, so we can use any of the 3 points to find that equation. And what we're trying to do, of course, is find when that is equal to 0, that is when the height is equal to 0. So let's now have a look at how we would solve equations of that sort. Here we have a typical quadratic, and when we want to find out when the y value equals 0, we are really just trying to find out where the graph cuts the x-axis, because along the x-axis y is equal to 0. We saw that we can solve a quadratic equation in the previous example where the height is equal to 0, either numerically from the table by extending it, or graphically, again by extending the graph, or algebraically. The algebraic technique is the preferred method because it's more accurate. And the algebraic techniques that we can use are factorization, completing the square, and using the quadratic formula. In this lesson, we will be concentrating on the factorization technique. That's usually the easiest way of doing it, but if we can't find factors, we move on to other techniques. We will look for patterns when we're factorizing, one of which is called a perfect square. It's called a perfect square because we have one thing, a plus b in this case, all squared. And we can expand that out geometrically by representing the a plus b all squared by a square of side length a plus b. Both the length and the width are a plus b, And so to now get the area of a plus b all squared, that is the area of the big square, we can break it up into its components. Here we have the a squared term. We have an AB term, side lengths there are A times B, and we have another one that's the same size, A times B. So we have two of those, that's our 2AB term, and we have a little square left of side length B, that's B times B is B squared. And so we can see geometrically there that A plus B all squared will give us an A squared, the first term squared, plus 2AB in the middle. That's 2 times the first term times the second term, plus the b squared, which is the last term squared. Another perfect square is where we have a minus b, so we've got a minus there in the middle. And we'll expand this out algebraically. Squaring, of course, means multiplying it by itself. And to expand those brackets, we need to multiply each term there by each of the other terms. And so we'll have an a times an a is an a squared. We'll have an a times a negative b is negative ab. We'll get another negative ab out of multiplying those two middle terms. And so we get negative 2ab there, and we get a negative b times a negative b is a positive b squared. Note that we always end up with a positive b squared in a perfect square. Now what we want to do is to be able to recognize the pattern of the expanded form so that we can factorize it into the bracketed form. That's called factorising. One more pattern we'll look at is called the difference of two squares. Again, we'll start off with the factors. This time it's an a plus b and an a minus b. They're not the same, so it's not a perfect square. And to expand that out algebraically, once again, we'll multiply each term by each of the other terms. The a times the a is a squared. That's our first term there in our expansion. We will also get now an a times a negative b. So that's our second term. We'll get an b times an a, so that's a positive ab. That's our third term there. And we'll get a b times a negative b, which will give us our negative b squared. Notice we're getting a negative b squared this time. Those two middle terms can cancel out. Minus ab plus ab cancels out. And we're left with just an a squared minus a b squared. Hence the name of the difference being subtract of two squares, the a squared and the b squared. So once again, when we're factorising, if we see this pattern of the difference of two squares, we will factorise it into an a plus b and an a minus b. Let's use those patterns now to solve some equations. In this example here we have an x squared plus 6x plus 9. The x squared, of course, is just x times itself, and the 9 is 3 squared. And in the middle we have 2 times that, 3 times the x to get the 6x. So we recognize that pattern of a perfect square, so we can factorize that into an x plus 3 all squared. Now to solve that equation, we take the square root of both sides. The square root of the squared term there just gives us the term x plus 3, and the square root of 0 is 0. And to solve that equation, of course, x would have to be minus 3. We'll look at another example, pretty similar to the one above, only this time we have a negative 6x. So the factors are going to be fairly similar to the previous one, except it'll be an x minus 3 all squared. Again, taking the square root, we'll get the x minus 3 has to be 0, and the x has to be 3. Let's have a look at another example. This time we have a 2 in front of the x squared, so that makes it a little bit more difficult. But we notice that 2 is a common factor out of all of those terms, so we'll take it out as a common factor. We can then divide by that 2 to simplify that equation, and we get this much simpler equation here, which we do recognize now as a perfect square because we have the first term squared, we have the last term squared is 5 squared, of course, and in the middle we have that 2 times that 5 times the x. So a perfect square is x plus 5 all squared. Again, taking the square root of that and then solving for x, we'll get x equals minus 5. In this example, we have the difference of two squares, an x squared minus a 3 squared. So our factors will be x plus 3 and x minus 3. We've got two terms being multiplied to give us 0, so one or the other has to be 0. In the first case, x would have to be negative 3, and in the second case, x would have to be positive 3. Let's see how we can factorize quadratics if they're not in that pattern of difference of two squares or a perfect square. Once again, we will start off with the factors and expand those out. So we'll have an x times x is an x squared, an x times an n is an nx, an m times an x is an mx, and an m times an n is an mn. We can combine the m and nx terms together. So if we're going backwards, we're really looking for the factors of the last term there. So mn will be some numbers, and we have to look for the factors, m times n. And those factors have to add up to that middle term, m plus n lots of x. And so the process is to look for factors of the last term that add up to the middle term. So let's try that out with this example. Firstly, we observe that it doesn't follow the pattern of the difference of two squares or a perfect square. So we'll try factorising. To do so, we will need to look for the factors of x squared. So that's x times x is our first term. And now we're looking for the factors of that 10 that will add up to 7. So we can easily say that that'll be 2 times 5. Now to solve that, once again, we've got two factors being multiplied to give us 0. So one or the other is 0. And in the first case, x would have to be minus 2. And in the second one, x would be minus 5. Let's try solving this equation. This time we have a 2 in front of the x squared. So we're really looking for the factors of 2x squared. That'll have to be x times 2x. Looking for the factors of the 6 now, we can have 2 times 3. But they're not the only combinations we can have. We can actually reverse the order there so that we'll have an x plus 3 and a 2x plus 2. They're different factors to the ones we had previously. And of course we can have a 6 times 1 or a 1 times 6. So we have to try all of these combinations out. Now when we multiply out the first one there, we'll get our 2x squared, of course. We now get an x times the 3 is 3x, and a 2 times the 2 is 4x. So the 3x and the 4x will give us the 7x that we're looking for. So that's our correct factors. If we tried one of the others, for example, we would have an x times 2 is 2x, and 3 2's are 6x, so 6x and 2x will give us 8x rather than the 7x that we're looking for. The other two factors won't work either, the other two pairs there. Now we can also notice that if these factors there were correct, that we could take 2 out as a common factor there, whereas we can't here. So that cannot be a factor, otherwise we would have been able to take 2 out as a common factor in the first place. And likewise with that last one, we have 2 as a common factor, so that can't be the correct answer either. So we have x plus 2 or 2x plus 3 equals 0, so one or the other has to be equal to 0. That's the only way we can multiply them together to get 0. So in the first case, x would have to be negative 2, and in the second case, the 2x would have to be negative 3, so x would have to be negative 3 divided by that 2. Let's go back to the tower problem that we had earlier. This was our equation here. The first thing we can do is simplify that by dividing throughout by a negative 5. Each term there is divided by negative 5. Now we're looking for the factors of negative 50 that add up to negative 5. So 10 times 5 is 50. If we won't make the 10 negative, then they'll add up to a negative 5. So our factors are t plus 5, t minus 10 equals 0. So one of those would have to be 0, one of those terms, and so the t would either have to be negative 5 or 10. So in this lesson we saw that we can recognize quadratics because they contain a square term. We saw from the table of values that the second differences were constant. We can solve quadratic equations by factorising, and we look for perfect squares, so they are of the form of the first term squared plus or minus 2 times the first term times the second term plus, always plus, the last term squared. They factorise into an a plus or minus a b squared. It'll be minus when the middle term there is minus. There's the difference of two squares where we have one term squared minus the second term squared, and the factors are a plus b, a minus b. And we can factorise our general quadratic as well. So when we have one like that, we are looking for the factors of that c, like for example m times n, that add up to that middle term. So the b has to be m plus n, and then we've found our factors.